Hey, so I'm re-recording this worksheet video because of what we shared in class earlier today, that it's possible to predict the product of an aldol condensation reaction, or for that matter, an aldol addition reaction, or a Claisen condensation reaction without going through the whole mechanism. And so in my previous iteration of this video, we went through the whole mechanism. I realized that takes a while. And just speaking perfectly practically, there is 50 minutes to take an exam and you have a limited amount of time. So we need some way to come up with the structure of the product, just like in these questions here, without going through the whole mechanism. And in so doing, we're going to have to draw some bad, horrible, blasphemous, illegal structures, but we will immediately correct our mistake. So if you'll recall what we said in class, here is a typical reaction, and it's asking us to draw the product. And so in class, we said that if you're given an aldol or Claisen reaction or Claisen type reaction, the way to know whether you're going to get an aldol reaction or a Claisen reaction is by looking at the structure of what you're given, and most particularly looking at the structure of the acceptor molecule, the one that's going to receive nucleophilic addition. If that molecule is an aldehyde or ketone, then you will get an aldol condensation reaction, always. And if that molecule is an ester, then you will get a Claisen condensation reaction, always. In this first problem, both the donor and the acceptor molecule are the same. So the acceptor molecule is an aldehyde. And in that case, we're going to get an aldol condensation reaction. So I'm just going to take a copy of this molecule over here to help us go through the steps, which we said there are but 2 steps. The first step is to make a bond between the alpha carbon, which here's your alpha carbon of the donor molecule, and we're going to attach that to the carbonyl carbon of an acceptor molecule. And the acceptor molecule is the same as the donor molecule. And again, in doing so, we are going to get a horrible, illegal structure. Carbon will have 5 bonds, but don't panic. We will fix the problem. So I'm just copying that down over here. Actually, I think I'm going to do it like this because I kind of know what's going to happen. Is that too many carbons? Let's see. Total, well, this is going to be a hydrogen over here because it was an aldehyde. And so I believe there should be 4 carbons total in that branch. 1, 2, 3, 4 in the original compound. 1, 2, 3, 4. So that's this horrible structure that we get. And then in order to go from here, it depends whether we're going to get the Claisen addition product, the aldol addition product or the aldol condensation product. If we need the aldol addition product, then we get rid of this horrible structure by simply converting C double bond O to C single bond OH. And lo and behold, we will then get a legal structure. And so that's what we have. That structure is now legal. That's the addition product. But we're given heat in this reaction. So it's going to dehydrate, and we're going to get the condensation product. And so in order to get the condensation product, which will be our final answer, what we do is we take the C double bond O or the C single bond OH away, and we instead make a new carbon-carbon double bond that connects what had been the carbonyl carbon of the acceptor molecule and the alpha carbon of the donor molecule. And so that's going to be your final answer. And that takes considerably less time than going through the whole mechanism. And I'll even double check myself just because I don't trust myself. Yes, and the answers, I didn't write the H, and you certainly don't have to, by the way. The H is understood since we're doing a skeletal structure. So that method works. And we had a similar method for a Claisen condensation. Here, both our donor and our acceptor molecule are esters. So the acceptor molecule is also an ester. That means that we're going to get a Claisen condensation reaction. And we're going to go through a pretty similar set of steps. There's only two steps. The first step in getting the product is to connect once again that alpha carbon to the carbonyl carbon of the other molecule. Just want to make sure I have the right number of carbons. We're going to get, again, an illegal structure with 5 bonds to carbon. So there's our carbonyl. That's the carbonyl of the ester. We're then going to have a methoxy group since it's a methyl ester. And then there should be a 3-carbon chain. So that's what we wind up with. And it is completely illegal and blasphemous and horrible. And then in the second step, to get the final Claisen product, all we need to do is delete the alkoxy group. There will always be an alkoxy group on that now illegal 5-bond carbon. In a Claisen condensation reaction, there will always be an alkoxy group there. There will be no exceptions. And all you need to do is delete it, and you get the product, and have corrected the problem of having 5 bonds to carbon. And I think if you compare that to what we got to over here, there is one additional issue, which is this is being very strict over here, but it is fair according to the rules. The rules state, or the instructions state, that you have to account for any applicable relative stereochemistry, just like we did with the aldol product. Here I'm comfortable predicting that this E-alkene would be the major product. I would predict that would be more stable since the two larger groups are trans to each other. Well, if there's any stereochemistry, we did just generate a chiral carbon. And I didn't show that initially. There's your chiral carbon. So for full credit, you will need to show one of the two enantiomers. So either this or this. That carbon is chiral, and so we need to account for that. So you would draw one of these two structures, just like it says in the answer key. Either one of the two, not both, but one of the two. And so, but we got there without going through the whole mechanism, which saves a considerable amount of time. So much for those questions. We then have, and as always, I've given you clues on where to start. We then have two mechanisms. First, this one, and then this one. This first one is going to be an intramolecular Claisen condensation reaction. The way we know that it's a Claisen condensation is because we're dealing with esters. And the way we know that it's intramolecular is because we're forming a new ring. So that ring can only happen by an intramolecular reaction. And recall, we want to make either a 5 or 6-membered ring. Here we've made a 6-membered ring. And in the way I've set it up, it's actually moderately obvious that we're going to form a bond between this alpha carbon to that carbonyl carbon. And so that's going to form our 6-membered ring. It's set up perfectly, as these intramolecular reactions always are. That's the reason that forming 5- and 6-membered rings is so favorable, because the atoms can form a shape that's very low energy. And then the atoms are just in exactly the right place to form those new bonds and close the ring. The second reaction looks like the reaction that we actually just talked about in class. This is formation of an enolate. There's only one place we can form an enolate, which is on this methyl group right here. Those are the only acidic protons in either of your two starting materials. That enolate we would then expect to add to the beta carbon of this alpha beta unsaturated ketone. And then after a couple of proton transfers, we would get this product. So that comes by combining both of those two molecules into one. So as for the intramolecular Claisen condensation reaction, we're going to start as we always do by deprotonating alpha to the carbonyl. We've already ascertained just by looking at the structure of the starting material and the product that we need to deprotonate alpha to this carbonyl and form the enolate that you see here. That enolate will then add into the carbonyl carbon where we've marked carbon 6. So we'll form a new bond between carbon 1 and carbon 6. I do really recommend numbering your carbons. Now remember, the way I've numbered these, we made this point in class, the exact way I've numbered these is arbitrary. You could have called this carbon 1 and gone around the other direction. It's fine, as long as you have a way of keeping all the carbons distinct from one another, and so you're clear on where you're forming your new bond. So we've just formed this new bond between carbon 1 and 6, and then just like in every other Claisen condensation reaction, we can reform our carbonyl very easily by losing an alkoxide ion as a leaving group. And that's always going to be the case in every Claisen condensation reaction, without exception. That will in fact give you a molecule that's identical to your product. But we do need to show this deprotonation. We've emphasized this repeatedly in class. We're still in alkaline solution. We haven't added the dilute aqueous acid yet. And we can't add the dilute aqueous acid early enough, quickly enough, to make it so that you don't have to show this deprotonation. If we attempted to do that, we'd wind up with an incomplete reaction, and we would get a mixture. So we need to make sure that the base does everything that it can possibly do. And one further thing the base can do is pull off this fairly acidic proton that sits between two carbonyls. And then, just like we said in class, I chose to move the electrons upward and form the enolate at the ketone carbonyl. You could just as easily have pushed them downward and formed the enolate at the ester carbonyl. It's fine. It's just another resonance form of the same species. So that enolate is what, however you choose to draw it, will in fact be what we're going to form next in the alkaline solution. And it's at that point, then we add the dilute H3O+, which again, we will add very slowly and carefully. We don't want to hydrolyze the ester, so we'll add it slowly and carefully, dilute aqueous acid. Probably if I were doing this in real life, I would lower the temperature by doing this in an ice bath just to make sure that I don't hydrolyze the ester. And so we just show the enolate getting protonated by a hydronium ion. We reform the carbon-oxygen pi bond. The electrons in the carbon-carbon pi bond then remain attached at this alpha carbon that's alpha to the ester carbonyl. We form a new bond between that carbon and the hydrogen of the hydronium ion, break the OH bond and release the water molecule, and then we get our product that way. So that would be the correct mechanism of this intramolecular Claisen condensation reaction. I almost want to go back and get rid of this horrible, no good, illegal structure. Yeah, just because I hate having it in the video. But that will work. That method we went over in class today will work. The next question is the addition of an enolate to an alpha-beta unsaturated system. And in this case, it's very clear where you're going to form the enolate. This methyl group is the only carbon that has any acidic protons in either of these two organic starting materials. So we start by using the base we're given. In this case, the base is hydroxide. And as always, we will not show the sodium ion. The sodium ion's irrelevant to the mechanism. It doesn't play any mechanistic role. There's no arrows involving an alkali metal cation. We just show the anion. And so we show hydroxide ion pulling off that acidic alpha proton. The electrons in the CH bond swing in between these two carbons to make a pi bond at the same time as we break the carbon-oxygen pi bond in order to get this enolate. And that enolate will then attack at the beta position. Enolates are a nucleophile much like cyanide or water or alcohols or primary and secondary amines. These nucleophiles, when you treat them with an alpha-beta unsaturated carbonyl compound, prefer to add to the beta carbon as opposed to the carbonyl carbon. And so that's what we show. We'll reform the carbon-oxygen pi bond. We'll break this carbon-carbon pi bond. The electrons in that bond will remain attached at this carbon and form a new bond to the beta carbon of the alpha-beta unsaturated system. That will necessitate us breaking this pi bond and shifting the pi bond over one place to be between now these two carbons, the carbonyl carbon and the alpha carbon. And at the same time, we'd better break the carbon-oxygen pi bond, otherwise that carbon will have 5 bonds. And while we did that briefly earlier in this video, illegal as it is, we certainly don't want to be doing that if we're drawing a mechanism. If we use it as a step to get a structure without having to bother going through the mechanism, we'll allow it. But if the point of the problem is to draw a mechanism, we'd better never have any pentavalent carbons. So this is the new bond we've got. And in so doing, we've formed an enolate. And so the only other step is to show this enolate getting protonated, and the only protic species we have is water. So we'll put a water molecule over here, emphasizing one of the OH bonds. We will reform the carbon-oxygen pi bond using an electron pair on the oxygen with a minus charge, so we'll get our carbonyl back. We will then break the carbon-carbon pi bond. The electrons in that bond will remain attached to the alpha carbon and form a bond to the hydrogen of the water molecule. We then release a hydroxide ion, and we get our final product. With that, wound up putting a hydrogen on this carbon, which is understood if you're using skeletal structures or line angle drawings. Whether you draw that hydrogen or not makes no difference. It's understood. And that's basically it. So that now I expect will be a much shorter video than my previous version of this video, but we will get this up on YouTube sooner rather than later. And that's basically it for our chapter 23 video. So thank you for tuning in. I look forward to seeing you all in class. And after this, we'll be starting chapter 14 on Wednesday. It's Monday as I speak, but on Wednesday, we will start chapter 14. So have a great day.